I love this last problem. I think it's really cool. A square is inscribed in a square sequentially as shown in the diagram below. If the sides of the original square measure 20 centimeters by 20 centimeters, write a series that will find the total area of all of the shaded squares, it should say. Find the sum of all of the areas if possible. Oh, buddy, it is totally possible, and we're going to do it. But in order to understand this series, I would recommend you try to understand how this image is made. So imagine if you start with your square like this, and then you break it up into 4 equal squares by cutting it like that. And then we're going to shade the bottom left square. So that would be like stage 1, if you think of this in stages. Okay, so let's think about this. At stage 1, which I'm going to label this, I'm going to go 1 right there. That doesn't look very good. How about some more complementary colors there? All right. Okay, so that will be stage 1. And if we go N to represent our stage number, and then the area at that stage, notice that at stage 1, and I'll put area there, at stage 1, the area is going to be, notice this is now a 10 by 10 square, so that area is going to be 100. Okay, so at the second stage of this game, you're then going to move to the top right square, and you're going to do the same thing. You're going to break that up into 4 equal pieces, and then you're going to shade in that bottom left area. So n equals 2 of this sequence, your area then is going to be, we started with that 10 by 10, then split it up again, so that's like a 5 by 5 square, so that's going to be 25 for your area there. The third stage of this game, same deal. Move to the upper right square, split it in half, shade the bottom left, and then that area will be the value of the third a sub 3, essentially. So if the last square was 5 by 5, this one's going to be 2.5 by 2.5. 2.5 times 2.5 is 6.25, I believe. And it's going to go on like this forever and ever and ever. You're going to create the congruent squares, shade the bottom left, split it again, shade the bottom left. Let's see how deep I can get. Split it again, and shade the bottom left, and that's definitely as far as I can go. But that's pretty good. So let's recognize this geometric sequence. And you obviously don't need to draw this all out if you're doing a problem like this. I just really wanted to show it. Oh, and I should have labeled this. I should have been like second, third, fourth, fifth, sixth. My bad. Whatever. Anyways, we want to add all these up because we're adding all those squares. So if you look at these numbers, 100 times 1/4 is 25. 25 times 1/4 is 6.25. Because think about it, 1/4 is 1/2 times 1/2. 25 divided by 2 is 12.5. 12.5 divided by 2 is 6.25. So our common ratio R is 1/4. Our first term, a sub 1, is 100. So let's write ourselves a series in sigma notation from n equals 1 up to infinity of our first term, 100, times our common ratio, which is 1/4, to the power of n minus 1, is going to equal, as we know, the first term, 100, divided by 1 minus our ratio, which is 1/4. So we have 100 divided by 3/4, which 100 divided by 3/4 is the same as 100 times 4/3. So we're going to get 400/3, which is approximately 133 and a third. Not approximately, it's exactly that. It's 133 and a third. But if you think about that compared to the total area of the original square, that's a 20 by 20 square, meaning it's going to be 400 total. And if you take the area that we have, 133.3 repeating, don't ever write a fraction like that, I'll be mad at you. And in fact, that's even stupid to write it like that, because look, if we take that value, which is 400 divided by 3, well, what's 400 divided by 400? 1. So that goes away, and you're just left with 1/3. So 1/3 of the square is shaded in. I didn't ask for that. I wanted the area, but I like the percent. That's cooler, better. Cooler, better. Cooler, better.